Okay, so we just saw the zeroth law of thermodynamics, and now we're going to dig a little bit further into its consequences. So what we saw is that we can group together, because being in thermodynamic equilibrium is a transitive relationship, we know that we can group together systems that are mutually in thermodynamic equilibrium, as they were in the same equivalence class. And this made us think that there is a physical property, there is a variable of state, or a thermodynamic variable, a new one, that reflects this. So there must be some physical property that if you measure it, if you look at it, all the systems that are in thermodynamic equilibrium have the same of that property. And this property is simply called temperature. So this is the way you introduce it to just define or postulate what temperature is. There exists a physical property called temperature, and those systems which are in thermodynamic equilibrium with one another have the same temperature. And as a variable of state, so this is a new variable of state, if you like I will write it here, variable of state, and this variable of state is intensive. Okay, it's locally defined, and this is something you of course know because you know about temperature. Then another important thing, now that we know what temperature is, we can say what thermodynamics is about, or what thermodynamics at least is good for. So before I told you that when you have like a piece of material, the variables of state which are relevant to describe it could be magnetization, could be the intensity of the magnetic field to which is subjected in case of it's a paramagnetic material, for instance. If it's a dielectric, well, also the electric field applied and the polarization, or the volume and the pressure. And if you think about it, you don't need thermodynamics for any of these things. You have been working with this kind of systems in electromagnetism, for instance, where you need, or when you need temperature for sure, thermodynamics for sure, is when temperature plays a non-trivial role. Okay, so this is the thing that makes you realize you need to go to thermodynamics. If temperature is not just constant and plays no role in the problem, but is playing a non-trivial role, then thermodynamics is the way to go. And there is another important thing, if you want to think about it, about thermodynamics, which is the name is very misleading, right? So thermodynamics. Okay, thermo. There's something thermal about it, but then there is this dynamics here, which really doesn't make sense, because thermodynamics, like I told you, is applied to situations in which temperature plays a role, which means temperature needs to be defined. And for temperature to be defined, systems have to be in thermodynamic equilibrium. But I told you that whenever you have dynamics, whenever you have a transient dynamics, for instance, going back to the example of the coffee, of the sensation of warmth, it means you are not yet in equilibrium. You are only in equilibrium where dynamics stops completely. And you are really in the asymptotic long time limit. So in a way, there's absolutely no dynamics in thermodynamics. And this is another reason why we like to call it thermal physics. Okay, so then we can discuss how we can access this physical property, because we postulate that it's there, but we need to see how we can somehow interact with temperature. And the way to go is to, of course, thermometry. So we can make thermometers, we can make systems to measure temperature. And so in a very abstract way, if you like, you just have to take any physical system you like, which is easy to work with, and identify a measurable macroscopic property that depends on temperature. For instance, in a liquid in glass thermometer, this could be the volume that a column of, say, alcohol or mercury occupies. And we know that expansion, thermal expansion and compression is going to make this volume change as the temperature changes, so it's a good indicator of temperature. And what I'm going to do is I'm going to set up a thermometric scale. So this is just a mapping, okay? So I will define in any arbitrary way I like a mapping, a function that will map the values of, in this case, the volume or the height of my column of mercury or alcohol into something that I will call empirical temperature for now. I'm not going to still yet say why I give it a different name. I don't call it just temperature straight away, but I call it empirical temperature, and I will denote it with a different letter. So this temperature is denoted by capital T, but here empirical temperature is, for our convention in these lectures, is going to be called lowercase theta. And by specifying this mapping, this function, I'm setting a temperature scale. So how do I, in practice, calibrate a thermometer? Okay, so what I do is I will choose a series of easily reproducible states of some reference system. For instance, the reference systems could be water, okay, just pure water. And I can take ice, water ice, and I can raise its temperature to the point of melting. And when ice starts to melt, I can say that this is a reference point, x1. And I will assign an arbitrary value of empirical temperature to this theta 1. Okay? And then, for instance, I take this reference system, or it could be a different reference system if I want, and I take it to another easily reproducible state. For instance, I take it to the boiling point. And that boiling point will correspond with a certain value of our observable property, and I will make some arbitrary mapping to some arbitrary temperature, theta 2. And then usually the kind of function that I will use in practice is going to be a linear function. There's no reason why we should prefer linear functions other than practical. Okay? If I had some nonlinear functional, then it would be really hard to calibrate the thermometer. Okay, so what I mean by this is that I will choose a function which is just ax plus b, and in particular I will say that f of x1, which is a of x1 plus b, equals, and I just define this to be the case, and I have a of x2 plus b equals the other temperature whose value I'm making up. Okay, so for instance, you know that the Celsius scale or the centigrade scale is assigning to the melting point of ice 0 degrees, but this is completely arbitrary choice. And then to the boiling point of water is assigning 100 degrees. Okay, and because the scale is linear, I know that the markings that I have to do in my thermometer from position x1 to position x2 are equispaced. And because they are equispaced, it is relatively easy to make these markings. If I were to choose a more complicated nonlinear functional here, then my markings probably would not be linear, equally spaced like this, but they will be maybe, I don't know, more spaced out as I go to the other point or whatever. So this is, of course, harder to work with. That's all. So it's a practical reason. Of course, there's several temperature scales. There is a centigrade scale, there is the Fahrenheit scale, and there are ways to convert from ones to the others. They are all linear. The ones that are popular, at least all the ones that I know of, are linear. And in our case in particular, we are going to work with Kelvin scale all the time. So this is going to be our reference, if you like. So we are going to adopt by convention the Kelvin scale, and the Kelvin scale is defined the following way. So it's defined in such a way that you assign to the triple point of water, so let's just write it, triple point of water, the temperature or the empirical Kelvin temperature to the triple point of water of 273.16 Kelvin. Okay, and otherwise you're going to choose your Kelvin degrees to have the same size as the Celsius degrees or the centigrade degree. Okay, so the transformation between Celsius and Kelvin is just a uniform shift. Let me just say what the triple point of water is quickly. Imagine that you have a container, and this container has some water ice in here. Yeah? So always there is certain pressure of vapor above the water ice. And if you raise the temperature of this system, if you make it feel warmer somehow, then this ice will start to melt, and just at the point when it starts to melt, there will be vapor water, liquid water, and solid water simultaneously in equilibrium with one another, and that is the triple point of water. It's a very precise point, and it doesn't depend on pressure, because for instance, when I'm setting up say this centigrade scale, I told you that the melting of ice and the boiling of water have these temperatures, but you may wonder, okay, but what is the pressure? Because I know that water boils at very different temperatures if I am at sea level or if I'm at the top of a very tall mountain, so it's something I need to specify. On the contrary, the triple point of water is just one, okay, and I don't need to worry about the pressure. There's only one triple point of water. So the temperature of the triple point of water, if I use the centigrade scale, is 0.01. Okay, so to convert between Celsius and Fahrenheit is, if I want the temperature in Fahrenheit, I have to write the temperature in Celsius and add 273.15. Okay, so remember this. And always remember that all the formulas that we're going to work with in thermal physics are going to be expressed in Kelvin. Okay, so always, if I give you a centigrade temperature, you have to make sure to convert that first before putting into any formula, to convert it into Kelvin, because otherwise it won't work.